everybody. So, like Andrew said, I have a background in physics and climate change, so this is a topic that's near and dear to my heart. And I'm just to give an introduction, I wanted to talk about this because I feel that a lot of the discourse around climate change is really wrapped up in politics. And you know, when you hear about climate change, it either makes you depressed or makes you angry. And so, but in my mind, talking about atmospheric science and climate change makes me happy because science is beautiful and physics is beautiful and the world is beautiful. And so I just want to talk about that. You know, it's something that we get to work on as a society, but that doesn't make it not fascinating and cool to talk about. So we've all seen well, any of us that have been in elementary school recently have seen a image like this. This is a diagram of the greenhouse effect. So all of our energy that comes to our planet, everything that sustains life and temperature on this planet comes from the sun. And some of that energy gets reflected, and that's pretty constant. And so is the amount of energy that we receive from the sun, actually, as an entire system of the planet. The amount, even during winter, etc. You know, during winter, of course, southern hemisphere is seeing summers, so the amount of energy coming into the system is basically constant. But the energy trying to leave the system is a dial that can be changed. And a lot of it, because a ton of it gets reflected back to the Earth's surface. Now, the amount leaving and the amount coming in have to balance. They have to reach equilibrium at some point, and they have on this planet many billions of years ago. So that is why we don't have a hellscape or a frozen wasteland, which is great. So anyway, as long as you understand that idea, that's the important part of the slide. So how does energy leave the Earth? Well, the answer is thermal electromagnetic radiation, which is very, very fancy science way of the physicists say that sounds smart, but it really just is that stuff glows when it gets hot. So, so this, we need to talk about what electromagnetic means, though. Electromagnetic radiation is really just talking about light. So this is a depiction of basically the different wavelengths of light and basically what we call them at different wavelengths. So radio wave, and this, as the wavelength gets shorter, the photons that carry the light have more energy. So that's why gamma rays are so dangerous. X-rays are pretty dangerous too. UV is a little dangerous. It goes down, and that's because these have tons of energy. And that is something that's important to understand. And going back to stuff glowing when it gets hot, one example of this that you might be familiar with is metalworking. So when metal gets hot, it glows in a color that we can see. It glows in the visible spectrum, which is a very small sliver of light right here that our human eyes can see. All the other types of light, we need machines to help us see. But this one right here is visible spectrum, and when you get metal hot enough, it starts to emit visible light. You also might know about the sun. You might have seen it before. It's pretty cool. It's pretty nice. Actually, pretty hot. It's 5,000 degrees, or it's 5,000 Kelvin, which is pretty close to 5,000 degrees Celsius. And because it is so hot, that's why it's yellow, because the peak amount of radiation that it emits is in the visible light spectrum, specifically yellow light. So that's why we have a yellow sun. But everything glows all the time. It's not just when it gets hot. Everything is always glowing, as long as it has any temperature at all above absolute zero, which means everything. Absolute zero is a stupid physics thing, don't worry about it. It doesn't actually exist. So everything has temperature, so everything emits light. Now the amount the amount of light and the wavelength of light that it will emit changes. So humans are about 310 Kelvin, so they emit infrared light, and we don't emit any visible light. But this is why when you use a thermal camera, you can see people in the dark. If you have a night vision camera, this is why it can see in the dark, because it picks up the infrared light that we are always emitting all the time. And the Earth is around that temperature too. So planets also emit infrared light. Now this is a diagram that, again, this is wavelength on the bottom here, so just like the last slide. And this curve is the light that the Earth basically would emit in an ideal circuit. If there was no atmosphere to get in the way, this yellow curve is the light that the Earth would emit, peaking in this 10 micrometer wavelength range. So, but this red is what it actually emits, and that's because a lot of these wavelengths are blocked by particles. So in the atmosphere, there's all sorts of stuff that can potentially block that light, but different molecules are transparent and opaque to different wavelengths of light. In the visible spectrum, for example, glass is transparent, right? We can see through it. But glass is not transparent in infrared. So things change what they're transparent to. So specifically, light, the infrared light that the Earth tries to emit is blocked by certain particles. You might be familiar with this one. This is carbon dioxide. And these are all lined up, so you can see that this is the percent absorption, and this peak here is from carbon dioxide. All of this light is blocked, so corresponding to this part right here. But you might not know that actually water is by far the strongest greenhouse gas. It's not close. It's extremely strong. It blocks so many of these wavelengths. The reason we don't really talk about that is because water is not really something you can change in the atmosphere. It kind of just does what the planet wants to do with it. But we do very heavily change the amount of carbon dioxide in the atmosphere. And actually carbon dioxide isn't necessarily it's a pretty strong greenhouse gas, but obviously it's nothing compared to water. The reason it's important is because the only band that water lets in is this small band, and carbon dioxide blocks that band specifically. And that's why we talk about carbon dioxide so much. We also have oxygen and ozone right here, and methane, and those block important parts of that window as well. But carbon dioxide is definitely the biggest player. So, all of this stuff that I've gone over so far was theorized way back in 1861. There, he's referring to carbon dioxide here. While an almost inappreciable admixture of any of the hydrocarbon vapors would produce great effects on the terrestrial rays and produce corresponding changes of climate. So he's saying right here, inappreciable admixture, very small amounts of burned coal, oil, that's what he's talking about, hydrocarbon vapors here, would produce great effects on the climate. So this is something that's been known for a very long time by the scientific community, which is really interesting. Part of the disconnect is that modern mathematical calculations based on his work, Tyndall's work in 1861, and also other important scientific work around that time by physicists like Stefan and Boltzmann. You might have heard of the Stefan-Boltzmann law if you take the physics classes. Substantially underpredict the atmospheric warming from a given quantity of CO2. In fact, it's by about a factor of 3. We see about 3 times as much warming as we would see from the basic mathematical equations that are outlined by Tyndall. So why? Does anybody have any guesses? Go ahead.
Because it changes how much water's in the atmosphere?
That is exactly right. That's one of the things. There's a bunch of reasons that is one of the most important. So yes, absolutely great job. So that's the first thing right here, water vapor feedback. As the atmosphere heats up, more of the water escapes from being a liquid and turns into a gas. So we spend more time with more water vapor in our atmosphere, and like I said earlier, water vapor is the strongest greenhouse gas. So that is what we call a positive feedback loop. Probably you might be familiar with feedback loops. Basically, it's something that is a cycle that makes itself stronger. So water vapor feedback is a very strong positive. There's also ice albedo feedback, which is an interesting one. As more ice melts, ice is white, and so it's very reflective, and so it will tend to reflect more of the sun's rays. But as it melts, it turns into water and ocean, which is much darker and absorbs more energy. And so that increases the temperature, which in turn melts more ice, and you get this feedback loop. It's not nearly as strong as the water vapor feedback, but it is present and important. There's also this is actually the biggest one out of all of these here. This is the biggest feedback loop. This is a negative feedback loop, so this one actually diminishes the effect. And this is called the infrared radiation feedback. And this one's kind of basic in a way, in that all it's saying is that as the planet gets hotter, like I was talking to you before, things that are hotter emit more radiation. So like the metal emits more radiation than a person, and the sun emits more radiation than the earth because they're hotter. As the earth gets a little bit hotter, it emits more infrared light, so that will tend to bring the planet to equilibrium. And so that's a very important effect. There's also this is a CO2 feedback loop, so basically, or this is a negative feedback. So not all of the CO2 we put into the atmosphere stays in the atmosphere. In fact, about a third of it goes almost directly into the oceans. So carbon dioxide dissolves in water, that's what soda is, and it does it naturally. So carbon dioxide naturally dissolves into the oceans, and so not all of the CO2 has an effect on heating the atmosphere. Also, here I actually forgot to go through these pictures. So it's a picture of the ice melting. Here's an image of different metals at different temperatures, emitting different metal levels of light. This is an image of the carbon dioxide here. There's less carbon dioxide in the atmosphere, so there's less in the ocean, but here we've added a bunch, but a bunch has gone into the ocean. And then lastly, the last negative one I want to talk about is a CO2 plant fertilization feedback. So as there's more CO2 in the atmosphere, plants actually become healthier. They become more capable of doing photosynthesis, and that reduces the amount of CO2, it puts some of the CO2 into plants. Because that's what plants are. They take that carbon, they disassociate from the oxygen, and they turn it into their trunks and leaves and everything. It's all carbon. So here, this is actually like a scientific study where they took a doubling. This is like a doubled amount of carbon dioxide that this plant grew in. You can see it's much bigger. This is just a rice plant. So in case I lost you on that slide, that's the correct response. This stuff's very complicated, and climate scientists also get sick of exhaustively listing all of the feedbacks. There's many more that I didn't even list. So they just lump it all into one number, the climate sensitivity, which is defined as the amount of warming we would expect from doubling pre-industrial CO2 levels. So that's about 280 parts per million. Current estimates put it at about 3 degrees Celsius if the amount of carbon dioxide doubles in the atmosphere. And again, the number that Tyndall and Stefan Boltzmann's calculations would have put it at, and that modern climate scientists agree with, would be the case if we didn't have any feedbacks. It would be about a third of that. It would be about 1 degree Celsius if it wasn't for all the feedbacks. So, changing gears a little bit, how else has the climate changed? There are many other mechanisms, but the most influential by far are the Milankovitch cycles. These are very cool. This is the primary reason that our planet has changed climate in the past. And the first one we're going to go over is orbital eccentricity, which again is a very fancy physics word for your orbit being an oval. So this orbit here has a very high eccentricity. This one has a eccentricity of about 0, or 0 because it's a circle. So now that you've been hypnotized by the great eccentricity diagram, this is what the Milankovitch cycle actually looks like. So as the planet goes around, and this is not to scale obviously, this happens over 100,000 years. This is a 100,000 year cycle before it returns to its original state. And the orbit gets longer and shorter. And you can see it gets a little bit closer to the sun here and a little bit farther from the sun here. And don't get confused, this is not how seasons work. In fact, right now, our closest approach to the sun happens during December. So, this is actually vastly outweighed by the tilt of the Earth. That's the primary thing for seasons. But this does have an effect, and right now it's making our winters milder and our summers milder. If it was the other way around, in fact it is in the southern hemisphere, it would make the summers more intense and the winters more intense. And that is important for the climate because when you have more intense summers, it's hard for ice to stick around. And like I was talking about before, the ice albedo effect means that if there's no ice, the Earth absorbs more total energy. So this has an effect on the climate that the Earth tends to be warmer when the orbit is an oval. Okay, the second one, there's 3 total Milankovitch cycles I want to talk about. This is the actual axial precession. So this is, I've actually already kind of talked about this because this is what changes the time of year that we are at closest approach to the sun. So like basically the Earth is spinning like a top over a very, very long period of time. Over 26,000 years, just like a top precesses, the axis spins in a different direction as it spins. The Earth does that too. And that means that in about half of this time, 13,000 years, the Earth will have its closest approach to the sun during our summer. So it will actually be flipped. And that will make our summers more intense, like I was saying earlier, and our winters more intense. And the effect that has is that because there's so much more land on the northern hemisphere, it encourages ice buildup and glaciation. And so when the northern hemisphere, our hemisphere, has more, gets more energy during the summers, that again feeds into the ice feedback loop I was talking about earlier. So this also has a big noticeable effect. And the last thing is the tilt. So our tilt actually changes as well. Right now it's about halfway between this, about 23 degrees, and but it goes from 22 to 24.5 degrees of tilt. And as the tilt is more, the seasons all over the planet in both hemispheres gets more intense. The seasons are, we get hotter summers and colder winters, and again, this feeds into the ice feedback loop I was talking about. And these are all pretty important effects. Don't be intimidated by this graph. It's not so bad. These are the three Milankovitch cycles I was just talking about. This is over the scale of about 800,000 years from here to here. And this is like the present, is this line. So when you take, like, these are basically the modeling the effects that these things have on our climate. And these two are just them multiplied together. So this is what they all are predict in aggregate. This is what they predict that the climate will do. And this is what the climate actually does. This is data taken from fossils, from benthic forams, which are, I won't get into it, it's a type of sea fossil that you can use to determine the temperature in the past. And then we also have a secondary source of that information, which are ice cores that we take. There are bubbles in that ice preserved that have ancient atmosphere preserved in them, and we can look at that and see what the past climate was like. And you can notice that these tend, say this line corresponds to this line. The model actually predicts the data that we see in the past with a fairly high degree of accuracy. So we know that this is a huge effect. Notably, you'll notice these big spikes tend to correspond with these other big spikes. And these are notable. I just want to give you a sense of scale. This spike right here is about an 8 degrees Celsius rise in temperature, which happened over about 10,000 years. So it's very slow compared to the warming we're seeing now, but it's a lot of warming. 8 degrees Celsius is a lot. And it turns out our planet is pretty resilient. We've never seen it heat up as fast as it is now, but when we've seen it heat up much slower, it can handle quite a lot and return to equilibrium, which is kind of encouraging, I think. Planet's climate is an elegantly balanced tug of war between a complex set of celestial and terrestrial forces. And ours is amazingly resilient in many ways, but it's our only home, so let's do what we can to take care of it.
Excellent. I think I learned a lot, but just hypothetically,
Yeah.
assuming you lost me on the whole thing,
Yeah.
with these Vostok cores, benthic forms, Milankovitch style, you lost me. What is one thing that you would wish we would all, if we remember nothing else, what's a big takeaway you want us to remember?
Science is cool.
Science is cool. Yeah, I'm so sorry if it was a little too much. I think the biggest thing is the fact that this is all it's not some black box that's hid somewhere. With the framework that you've gotten here, I think you can do maybe a few hours of Wikipedia research and come to a better understanding of all this stuff. It's not that hard. Literally, the equations I was talking about are literally just multiplying 4 numbers together. It's not calculus. It's all this stuff is stuff they could easily do in 1861, and it's really interesting. And it's not something we just have to take for granted. It's something we can actually figure out how it works for ourselves. So.
First off, I feel like I went to the store and picked up one of those yellow books, Climate Change for Dummies. So thank you for simplifying this about it. It was digestible, and hugely interesting. Yeah, great job on that. So maybe this is an oversimplification, but that's why I'm positive for your guidance. There's so much rhetoric and things. We know climate change is happening. But am I to take away today that the proponents or the influencers of climate change aren't as potentially egregious as is being stated of all of this methane and all of this? It's possibly more our planetary rotation within rotation within rotation, right? So rotation and distance and I don't know, all right, centrifugal pitch and all of that. Is that an oversimplification? Some of this is going to happen no matter what we do. And I'm not saying that as a pass card, because I still believe in protecting Mother Earth and being a good steward.
Yeah, I mean, the Milankovitch cycles, maybe I didn't give it enough of a sense of scale. All of those happen over tens of thousands of years. So they certainly aren't responsible for the warming we're seeing now. In fact, they're going the other direction from what we would predict based on the Milankovitch cycles. That's just to give you an idea of why the climate has changed so drastically in the past, which is often a thing that gets touted by people that are saying that climate change is not a big deal because it's happened a lot in the past. And that's true, but it's happened over much longer
We're
time.
not arguing climate change, we're actually discussing the influencers of climate change.
Yeah. So I would say that it depends. So I think that the people, another thing I want you guys to take away from this is that you can trust the physicists and climate scientists when they talk about the science, okay? There are opinion-based things, but it's more to do with how bad it's gonna be. For example, one thing that's not known very deeply by climate scientists, and they'll tell you this, is Venus. What happened on Venus is it had a runaway greenhouse effect. So the more water vapor entered the atmosphere and this heated the planet up more, the feedback loop we were talking about earlier, but it kept going. It wasn't self-regulating, and all of the ocean boiled. And now it's just a hellscape. So it's not completely known that like, most climate scientists agree that that probably can't happen to Earth, but no one really knows. So that's really the area where it's more up for opinion and discussion and philosophy, is like, what do we do about the stuff that we don't know? The stuff that we do know, but we don't know everything. So, you know, there are people, I do everything I can for the environment. Me personally, I'm very liberal. I love taking care of the environment and doing what I can and spreading information about it. But, like, I admit that there are things we don't know, and there are people out there that believe what I believe and don't really say when they don't know. And so be a little skeptical, I would say, but generally I would say that climate scientists, if they have credentials, they're very conservative with their estimates. So.
Thank you.
So that kind of touches on a little bit of what my question was, is
Yeah.
that like, I hear a lot of rhetoric around not quite the Venus level runaway,
Yeah.
but just sort of like the quote unquote point of no return for pre-industrial levels.
Well, we've certainly hit a lot of points of no return already. There's a lot of animals that are extinct already. A lot of ones that we teach about kids in schools, we're gonna have to take out of textbooks or tell them that it's history. Like, you know, cheetahs are kind of on their way out, for instance. In fact, we currently on the planet, there are approximately, I think it's something like 30%. Only 70% of all mammal life on the Earth has died out. That's not species. That's saying there's only 30% of the mammals on this planet that are non-human and non-farm animals that there were before the industrial time. So we've killed 70% of animals on this planet through our actions and urbanization and everything. So we've definitely hit a lot of points of no return as far as the ecosystems go already. But we don't know. The ecosystems are extremely complicated and not subject to simple math like the climate is. So that's something that's a little harder to know. Is that gonna be doomsday for us or not? I don't know. I don't think anyone knows.
Just also one more thing that I just wanted to add is that Venus didn't have like plant life as part of the self-regulation.
Well, yeah, certainly. Yeah, we don't know what happened, what was going on in Venus. We don't know much about it, but that's yeah.
Excellent presentation.
Thank you.
And I've been paying attention to this for many years. But I was wondering, it seems like it'd be good if there could be some sort of chart or something to show the magnitude of these effects. You talked about the way the Earth wobbles and so forth, how close it comes to the sun,
Yeah,
and a lot of other things like maybe sunspots.
yeah,
Various cycle for sunspots. And I guess my thought is, and maybe a question, is there a chart or something that shows the magnitude of the things that happen, such as CO2 in the atmosphere, such as sunspots, such as the Earth's change in its wobble?
Yeah.
So that one can then see that, yeah, these are real effects, but they're minor compared to the others that we can do something about.
right.
The Earth is warming, but we can't do anything about it because these things are affecting, is what I hear sometimes.
Yeah, I mean, that's a great question. I didn't include them in here, but you can easily find charts that plot, like, on top of each other, the history of the temperature of the Earth and the history of the CO2 of the Earth. And you can see that they correlate quite heavily. And you can also, like, add on the Milankovitch cycles that are predicted and stuff like this. But yeah, that's actually, when I talked about this, the climate sensitivity being about 3 degrees, that's been estimated in a lot of ways. It's been estimated through computer modeling, it's been estimated through an attempt to do the math on all of the feedbacks, it's been attempted to do on examining historical data, which is kind of what you're talking about. And they all come to about the same amount. It seems that when we put a certain amount of 280 parts per million into the atmosphere, it rises by 3 degrees Celsius. No matter how we spin it, no matter how we look at it, that's the number we get out. So we do know that pretty well. That's the thing. And honestly, again, the warming effect that's happening today is we've we've seen about 1.5 degrees Celsius rise, which is nothing compared to the 8 degrees, right? The important part is that it's happening in 100 years as opposed to 10,000 years. So it's the speed at which it's happening that has people worried, because this is never, we don't think this has ever happened on Earth before.
It seems pretty clear that we should tax sources of methane and carbon dioxide to fund sequestration, fund cleaning it up. What are your thoughts on an approach like dumping phosphorus in the ocean to fertilize blue-green algae or something to sink all the carbon?
I mean, I don't think it's particularly wise to play God when we don't understand the systems involved. They're very complex. That's just my take on it. I think that the first thing we need to do is stop emissions, personally. I think that that's the best and most reliable road to an Earth that we understand and the climate system we understand. I think that things like that can be talked about, but we have to be very, very careful that they don't have unintended consequences that destroy fishing, the fishing industry, and start millions of people. Things like that are very important, obviously.
First of all, thank you so much for explaining the principles of climate change to a T without getting too complicated into it.
Did my best.
Well, that's all right. So if you go back to the spectroscopy slide where you show the absorption spectra of different gases.
Ooh, there it goes. Yeah.
So as of right now, there is only 0.042% of the atmosphere that is made up of carbon dioxide, and yet that 0.042 contributes to that big absorption band. Yeah, that's the power of quantum physics.
Yeah.
Working to make that happen. So
Absolutely.
it's already absorbing most of that energy in that band, and as we continue to add carbon dioxide to the atmosphere, that curve isn't so much going to grow in height, but rather in width.
Right, like these little tiny peaks are going to become giant peaks, for example.
Those are going to become bigger.
Yeah.
But would we expect the warming effect of CO2 to slow down with concentration?
That's a great point, and absolutely. We don't, the climate sensitivity that I was talking about is very carefully worded, that it's the difference that happens, and I kind of missaid this earlier, it's the difference of the warming you get between 280 parts per million and 560 parts per million. So it's not saying this is how much you get if you add 280, it's saying this is the amount that you get if you double, to do that specific increase. So because it probably will change, and we know that it does change depending on how much you have. We've seen that again in the climate record and all these things.
Have you seen new technologies that get you excited about our hopes for the future? Like, are you familiar with barium sulfate paint or other things that increase emissivity in that narrow window that we can still get infrared out?
That's it's a great point, and there are a lot of technologies that are very cool, and I think are very important to investigate. And I don't investigate those as much, so I can't really speak to that. What gets me excited is going to sound very trite, but solar panels. Those are the secret to our future. We don't even need batteries yet, because we use so much more power during the day that just having solar panels lets us turn off power plants during the day and not even have to have batteries. So solar panels are extremely cost efficient over their lifetime compared to even coal, which used to be the cheapest of all. And so I'm very excited about the economic changes and the social changes more than anything. I'm excited about things like people starting to use white tiling on their roofs because that reflects more of the sun and lets them use less heat in the summer, or less air conditioning in the summer, which can save a ton of stuff. Like social and cultural changes, and also especially pushing corporations. That's the things the social are the things that get me the most excited, because those are the things that are having positive effect now, basically.
So on the slide where you showed the cumulative effect of the 3 or 4 different cycles, it seemed like we would expect to be peaking. If I saw that slide correctly, which means, and this is the question that I have, is am I right in thinking that means that we are adding additional forces in the heating direction at the peak of the cycle, which is going to push us outside anything we've seen before in the recorded history of the cores and the forums? Is that correct?
Yes, that is a great point, and absolutely true. I will add, just as an addendum, note that this graph cannot possibly show the fine details, because it's so, and this is 10,000 or 100,000 years, just this little spot. So we're actually on a downtrend right now, but yes, we are still at the peak, and when the Earth was trying to cool overall, heating it back up could have unknown consequences for sure.
I have a question about the CO2 plant fertilization. When those plants that consumed that carbon die, does most of that go back into the atmosphere, or is it sequestered somehow?
Yes, that absolutely happens. So when trees burn or are decomposed, all of the carbon that was in them goes back as CO2. So this is why planting trees is actually not particularly helpful unless you have a way of making sure that the trees you planted stay a forest and that they weren't going to be a forest already. Because the only way to permanently, plants, yes, we think they eat CO2, but then they die and they return it back, and it all comes out in wash in the end of the day. So that's a great question.
One last question.
So I was really interested to hear you talking about solar panels, because my dad recently, bought some solar panels and was talking to me about this deal that sounded like almost too good to be true. So I was looking into it. Basically, he's getting a really good deal up front, but has to pay for it over 30 years or whatever, right? Basically is committed to this thing. And I was sharing my concerns about that, because as someone who knows how the internet has moved, right? Imagining signing up for a 30-year dial-up deal over, right? And it makes sense that you would do 30 years over a house, because it's not going to change. It's never going to move. It's just right there. But as technology gets better, do you have a concern with things like solar panels on houses and these kinds of deals where they're, or do you feel like the technology is good enough that that's okay and it's not going to shift too much?
Yeah, no, that's a great question. We have reached somewhat of a plateau, but we're not quite there yet. So there are improvements to be made. I don't think we're going to see a doubling in efficiency or anything like that from solar panels, but they are going to continue. They do seem like they're going to continue to improve for a while still. I would say definitely take those into account with caution. Also, we don't know necessarily that those panels, unless you're buying from a company that has been in solar for 30 years, you don't know that their panels are going to last 30 years necessarily. So there's that to take into account. But I will say that the thing that's the most daunting about solar as a residential investor, or even as a company that wants to build solar panels as part of your business, the thing that often pushes decision makers away from solar and wind is that all of the cost is up front. Yes, it's the cheapest if you take energy over its lifetime divided by the cost over its lifetime. It's the cheapest, but all of that cost is up front, and money now is worth more than money later. So that 30-year deal, I think that being cautious about it is warranted, but I think it's a great mechanism for people that want to get into solar and want to see those returns 10 years down the line when they pay themselves off. they want to see those and don't have the cost, the money to do it for it up front. So I think I'd be skeptically optimistic about deals like that.
All right. Thanks, Amy. That was so great. Good one.